comma, f2, which is just a function of a minus cb. So then what? Now you got to run it through this thing, right? I suppose. Then what do we get? We get 1/2 of, I'm going to write this in 2 lines, f1 of a plus cb plus f2 of a minus cb plus 1 over, rather k, over 2c, parentheses, f1 of a plus cb minus f2 of a minus cb. So because there's an isomorphism of the algebra with k squared equals to c squared, and the direct product algebra, it says something about the structure of a differentiable functions. It says any one of them can be rewritten in this kind of form. There's some real function f1, there's some real function f2, such that you can, form the solution by taking this linear combination or difference. Like in particular, this says, because of our previous work, right? We get solutions to the wave equation from this, right? The wave equation here is, let's see here.
Almost looks like the way you represent a function in a way that it's even and odd part.
What's that? Yeah, right.
Structure.
It's a lot like even and odd, isn't it? Yeah. Let's see here. So we have k squared, right? Minus c squared equals to 0, which says what? It says that g, in my current rather silly notation, I guess it says GAA. Wait a minute. Oh, no. That says that G, because this is the second one, right? So it says GBB minus C squared times GAA equals to 0. All right, I need to do a translation of letters, otherwise I'm going to go nuts trying to explain this. If you don't mind, I'm going to make a translation here. And here's my translation. We're going to, hope I choose wisely. Yeah, we're going to let B equal to T, and we're going to let A equal to X. Okay. So we've got this equation. We've got G TT equals to C squared GXX. This is a wave equation. With speed what? C. You can do dimensional analysis here. So meters squared over seconds squared, and then that cancels the meters squared by the twice differentiation. So we have like total dimensions of 1 over second squared here, likewise over here, 1 over second squared. I guess it's meters because G has units of meters usually. We talk about the height of the wave as a function of its position. These are transverse waves, right? So we're talking about
What do you mean when you say wave equation with speed c? What does that say? Like,
Wait, is that the speed of light maybe? Is it like light waves?
well, C is just a letter.
Oh, okay, you're just...
oh, okay. I was thinking like
You
speed
could
of light.
make C be like V, but I didn't do that because we've been using U and V as variables.
Yeah. Okay.
So the real and the k-imaginary, sorry, it's awful, the k-imaginary component of G, real part of G is what? 1/2, right? You can absorb the half and the C into the functions, right? So let's just, if you'll allow me, I'm just going to abuse notation and say F1 bar. That's not an abuse, actually, it's just annoying. F1 bar, A was what? X plus CT, right? Plus F2 bar of X minus CT. And then the imaginary part, if you will, of G is what? Again, it's F1 bar, F1 bar of X plus CT minus F2 bar of X minus CT. Of course, if you wanted to think about these separately, you could just redefine F2 bar and throw the minus into that if you wanted. What are these? Think about it in the... So if we think about this in terms of the, let's say, y x plane, right, and think about y equals to, real part of G, for example. What do you got? What is this? And what is that? If I told you had y equals f of x minus 3, you know what it was. It's y equals f of x shifted 3 to the right, right?
Mm.
So this is y equals f2 of x shifted CT, right? So if C is positive and time is positive, right, if you think about time flowing into the future, what this is it some whatever, y equals to f2 of x, f2 bar x minus CT. It's some sort of waveform, and it's traveling that way with speed c. You see that?
Yeah.
What's the significance of the other term? It's a wave traveling the other direction. The other one's a left-moving waveform. And this says that any solution to the wave equation can be decomposed into the sum of a right-moving and left-moving wave, whose shape is completely given by its initial waveform at time 0, I believe. Well, that's not quite true, because at time 0, the left and the right moving waves are both superposed, so you'd have to know which one is, I guess we need more information in order to tell which part of the wave was going that way and which part was going that way, right? If you got two pulses at the same time, one's going one way, one goes the other way. If you just knew what their initial shape was, they're all intertwined, so you can't tell what F1 bar and F2 bar is, but this is actually a classical method to solve the wave equation. You suppose the solution has the form x minus vt, some function of x minus vt plus some other function of x plus vt, and you plug it into the wave equation and work with the given initial waveform, and you can figure out what the unknown pair of functions, which I've called f1 bar and f2 bar are. But we have just derived this by exploiting the isomorphism between the K algebra and the direct product. So, again, I think this is more or less in Waterhouse's paper, but I'm fond of it. All right, so we got what, like 10 minutes left? Is that right? Is that fair?
Yeah.
Okay. What we need to do to go further in the method is we need to figure out how hyperbolic functions transform things. Right? So let's start with a simple example. What does it look like if you just multiply by a hyperbolic number? I mean, you guys know what happens if we multiply complex. If we go from z maps to cz, all we do is we dilate, we expand by the magnitude of c, the modulus of c, and we rotate by the standard angle.
Right.
That's the effect of multiplication by a complex number. Question, what's the effect of multiplication by a hyperbolic number? I don't know. I'm about to find out with you. Exciting, isn't it?
Do we have, I remember you writing it, do we have something analogous in hyperbolic numbers to the Euler function? Like the e to the I theta?
Yes, but I
That's
don't.
Pretty.
I'm not confident about the existence and the use of a polar representation.
Right.
So, I mean, there might be something like that. Nathan's trying to do that,
Right.
but there's some wrinkles. I forget, but let's just work it out directly for the moment. So, but that's a very good idea. So we want to map z to, say, a plus bj times z. So here we're looking at x plus jy, right? And we're mapping to a plus bj times x plus jy. What happens? I mean, that might be worth what you just said. I mean, we gave up on polar representations for more complicated algebra. We might have some kind of pseudo-polar representation for, let me think about it for a second here. If you imagine doing the same calculation in the complex numbers, this also wouldn't tell you much.
Right.
Right? I mean, it'd be the same formula, but with a minus here. It would be obvious to you that that's a dilation times rotation. Not really. But I suppose we can rewrite this. It may be instructive to use linear algebra here, actually. This is, what is this? Well, this is A, B, B, A, times xy, right? So what is it? What does that matrix do to points?
I mean, obviously we know it multiplies it by some sort of magnitude. It's kind of easy to see, right? Because the determinant isn't always 1. So we know it's going to scale it by some factor. But
let's see if we can look at I mean, of course, if we put well, I mean, yeah, okay, fine. We put b equals to 0, then it's just a dilation, and it maintains the direction, right? So we've still got pure dilations, like just expansions and contractions, like just like in the complex geometry.
Right.
The question is, what does multiplication by j do, right? Let's look at that specifically for a second before we'll come back to this. But you know, if I take x plus jy and I multiply by j, what's that do? Hmm.
And then just kind of flip it in some way with the axis.
Yeah. Let's try to picture that. What happened? We went from. And I just draw a symmetric point. I'm an idiot. We go from xy, right? X plus yj, and then multiplication by. Where'd multiplication by j take me?
Doesn't that just flip it over the diagonal of the quadrant, right?
Yeah, the x. I think you're right. So it's just over here symmetrically. So.
Yeah.
Yeah. This is fantastic. Because this means that we can take the things we've done here and just flip them over
So we get
like
a
that
lot
to
more
get,
of the plane.
and then I think it means that. I'm not. I gotta think about that some more. But I guess that's also a motion you can get with a complex number, right? Like, for what it's worth. But
But the complex number would be kind of more difficult to find, wouldn't it?
yeah. Yeah.
Yeah.
Well, right. I mean, for that. Okay. Yeah, you're right. For if I think about how it works on all points,
It's gonna be a lot more difficult to find. You'd have to.
for a fixed complex number, the motion of multiplication by that fixed complex number is not the same as this.
Yeah.
Agreed. Multiplication by j takes, the points below here, it takes this side and flips it up there, and it takes that side and it flips it down here, doesn't it?
Mm.
So this is really what your project's about. Okay, now we've finally gotten to the point.
Right.
This is what I don't know about. I just haven't played enough. And these aren't particularly hard things, but they just require some kind of like sitting and playing. I would think about multiplication by a hyperbolic number. That's the simplest thing I can think about. How about inversion? 1 over z. What does that do? And you want to pick something that's manageable, like a circle or a square or a vertical line segment or a horizontal line segment, and see how it transforms. And just make yourself some specific questions and just take it one investigation at a time and tell me what you find. And I think if you get enough of these, then you can combine it with these ideas over here to actually do some hyperbolic conformal mapping.
Connect some of the dots a
Yeah.
little bit.
I'm not looking for you to develop the entire theory of hyperbolic mapping. What I'm looking for you to do is to find some explicit and interesting examples of hyperbolic mappings that we can show people. Does that make sense?
Yeah. I mean, that's what it does to elements in the first quadrant. So.
What are the eigenvectors of that?
Oh man.
Eigenvectors are the fixed points of the mapping.
I mean, the eigenvalues are just going to be all the points that lay on the 45 diagonal. So all the points where x equals y. Right?
Or minus y, I think.
Yeah. Well, yeah, the diagonal including. In the
Oh, that's funny.
diagonal
You
axis.
saw that from this, but I'm talking about for A and B.
Oh,
Find the
yeah.
what?
Well, I mean, geometrically, like.
Yeah, but this is a specific
Yeah,
example,
yeah,
right?
Yeah.
I think it happens that I believe in my heart. I could be wrong. I mean, what are the eigenvectors of A, B, B, A? I think if you think about it, if I do 1, 1,
Mhm.
right? 1, 1 times AB gives me A plus B, B plus A,
Mhm.
right?
Yeah.
What if I do 1 minus 1? I get A minus B, and then I get B minus A, which is minus 1, which is A plus B times 1 minus 1. So 1, 1 and 1 minus 1 are eigenvectors of AB, BA. With eigenvalues 1 and minus 1, that's it. Those are distinct. Those eigenvectors are linearly independent. Those are the only directions which hyperbolic number multiplication fix, you know? I should make that a linear problem, you know?
Are you teaching this?
Man, I wish I just had a week to sit and play with this stuff. It'd be fantastic. Oh well.
I want the job.
You guys are lucky. I can play.
I even have a whiteboard in my dorm room too, so it makes playing easier.
I wonder what the square function does. I mean, we know what the squared function does in the complex, but it may be worth to invest. Like, okay, so just let me take a second here. So if you have x plus jy, can you write it as e to the j, beta times some radius rho? Is that possible? And is it useful? I mean, it is useful to study the square function if it's possible, because when you square that, this squares to rho squared,
Right.
e to the 2j beta. Because I will tell you, the exponential function works like normal over the algebra. You can check on it, but it's true. So, yeah, but this, and to figure out how x and y are related to rho, you can figure that out pretty fast. It's just going to be cosh beta plus j rho sinh beta. Some of this I've done before. So you got to be able to solve x equals to this and y equals to that, So that means that the hyperbolic tangent of beta is equal to the quotient of y over x. It means that rho, rho is going to be related to like the difference of the squares of x and y square rooted or something like that. But this is not a global formula. It's only good for like a quarter of the plane or something.
Right. Because of all the weird angles.
You'll have different hyperbolic representations in different sectors. This I know because I tried to write up a hyperbolic coordinate section for Calc 3 notes about 8 years ago. It didn't go well. It's because the hyperbolic coordinate lines are not orthogonal. Like the lines of constant rapidity and the lines of constant, I guess I called it whatever, C or something, these do not meet at right angles. So it's not an orthogonal coordinate web. So when I tried to use, I assumed some of the orthogonal coordinate formulas in my thinking, and it all blew up in my face. So I was very happy with Daniel last summer when he worked a problem like this, and he noticed that it wasn't orthonormal, so he adjusted accordingly, and it still made something work. I forgot what that was. I was very happy with it. But anyway, I guess I gotta go home. Otherwise, I'll turn into a pumpkin or whatever.